Okay, good afternoon, everybody. We are happy that we have the crew from D WAVE here today as guests. In particular, Eric Ladizinsky, who is a co-founder of D WAVE and their chief scientist. I think your main task is really shepherding the manufacturing of the D WAVE chips. And to say a few words about Eric, he's actually here from the neighborhood. He went to UCLA, but then moved to TRW, where he was working on superconducting electronics for next generation supercomputers to extend Moore's law past CMOS. And then at some point he had an idea that these superconducting circuits would also be quite useful to build an actual quantum computer. And he won in 2000, I think that was a very large DARPA grant to pursue this exact idea. So he formed this mini Manhattan project to build quantum computers based on superconducting electronics. And then in 2004, he hooked up with Geordie Rose, the other co-founder of D WAVE, and then within a company context, continuing this vision to build such a computer and have sort of all the necessary disciplines of science and engineering together to pull this off. And as you know, one of these machines we have in the Quantum AI lab is sitting over at NASA Ames, and we have, of course, a lot of fun with your chips, experimenting with them, essentially probing a functional role of quantum effects in computation and blueprinting elements of quantum annealing, quantum optimization algorithms. But of course, to build a serious computational advantage or capability, these chips will have to undergo more evolution. And that's what we are going to hear from Eric today, how D WAVE and Eric's crew is planning to evolve scalable quantum computation.
Okay. Thank you very much. First I'd like to say, it's really gratifying that we built something and created an effort that people are interested in. There's been tremendous progress over a relatively short period of time. I'm really personally gratified that we have all these brilliant people at various organizations, the USC and ISI crew, and NASA and Google, because a project like this really takes a community of researchers to bring it to fruition. You know, in the early days of microprocessors, they weren't computers like we know them today. They were controlling elevators and things, and it was a lot of people who started looking at this nascent technology, figuring out what you could do with it over time. So I'm enormously gratified that there is a community like that that's taken interest, and I think this will help us get to where we want to go. I've called my talk Evolving Scalable Quantum Computers because at D WAVE we've taken this evolutionary approach. And I'll tell you what that means. But first, why quantum computing? So I'm assuming that some of the people that I'll be speaking to in the audience, they don't really know what a quantum computer is. They're kind of mysterious. There's a lot of complexity there. I'm going to try to make it as simple as possible and tell you a little bit about it. Now, why is there excitement in quantum computing? And this is kind of my perspective. Every once in a while, humans learned there were these physical phenomena that were around them, but we didn't know how to harness them ourselves. Obviously the first one's a big one, fire. But it was hard to make. So it might occur naturally, but I haven't actually harnessed it for my own use. And after a while, we learn how to do that ourselves, whether it's agriculture or tool making or electricity. And once we harness those and we know how to control them in a detailed way, obviously it's game-changing for our species and our capabilities. I think that quantum computing, if realized at scale, could be this kind of thing. It's harnessing phenomenon that are fundamental to everything in our universe, quantum phenomenon that underlie the structure of matter and radiation and everything that we know. And people talk about it like this. There's a great deal of excitement, so it tends to bring in some of the most brilliant people from a whole set of disciplines in physics, computer science, and it could have a big impact. Now, there's a lot of hype around it. So how do you actually make this happen? And why is there this interest in quantum computing? What do we need bigger computers for? We have these giant centers with Titan supercomputers that do petaflop scale computations. So what do we need more of that for? Well, the interesting thing is that if you look at the top guy, I think, do I have, there's my laser. All right, so this is a plot of the number of electrons involved in switching a transistor from on to off, okay? And so the number of electrons per switching event is getting smaller and smaller. The devices are getting smaller and smaller, and you're getting more and more of them. And there's going to come a point where rapidly approaching, sort of atomic dimensions as a natural limit to the size of transistors and memory elements. We already have single electron transistors. We just don't use them at scale. Okay, so wow, we should be able to make some really powerful stuff, and then we can have three-dimensional circuits with these single electron transistors, and imagine what we could do and scale up giant data centers. The interesting thing about that, with all of that, there are still problems that would forever remain beyond our reach as humans with all of that. And so there's a field that's called complexity theory. And what people do is they look at a model of computation, say the Turing model of computation. We have a mathematical model that captures the idea of what it means to compute. And we can use that model to say, what are the ultimate limits of computation based on this idea? And then using that model, theorists have created these classifications for what's considered tractable, like something that we could actually do reasonably, and intractable. And this is kind of an artificial definition, but it's useful to write theorems. We tend to look at not how long a given problem takes, but how much harder a problem gets in terms of the resources required, in terms of the time it takes to get a solution, or the amount of energy it takes, or memory requirements. And in this case, I'm looking at the time to solution. And I look at the time to solution as a function of how big the problem is. And I look at how the resources scale up as the problems get bigger. So this definition from complexity theory is that problems that scale like a polynomial in the input, like say, there's n to the fifth. That's pretty bad, actually. But let's say you doubled the problem and it was 4 times as long to get a solution. That's like n squared. So problems that scale like that are called polynomial time scaling, and we call those something that we could achieve maybe by throwing a lot of resources at it if we thought it was worth it, right? Now, obviously, n to the 10th is pretty bad. But there's another class of problems where the time to solution scales exponentially with the size of the input, like 2 to the n, and we call those intractable at large scales. Because as I take all of those single electron transistors, 3D processors, and I scale them out, they kind of scale linearly. And I'll never catch problems that scale exponentially. And it turns out that a lot of really interesting problems, high-value problems for us to solve, are of this variety. They scale very badly. What kind of problems are those? Simulation of quantum systems. So when people want to do quantum chemistry, when I want to know, I put some atoms together and want to know how they fold up into a protein, and the shape of that protein confers its biologic function, you can't do that for very big molecules at all. Detailed chemical reactions, if I want to make better materials, I can't model these on computers sufficiently. People try, but they have to make tremendous approximations and don't get very good results. And the reason is that these, at those scales, at those molecular scales, you're getting quantum mechanics involved, and classical computers can't solve these in reasonable time frames. Another class of problems which we're interested in at D WAVE, and you guys here at Google, is complex combinatorial optimization. Okay, sounds like a mouthful, but all it is I have a whole bunch of ways that I could do some complicated thing, and there's a best way. So a mundane example, for instance, would be FedEx wants to route all of its trucks and airplanes. How do I do that routing? I have this exponentially growing tree of possible routing strategies. Which one do I choose to minimize fuel consumption? They can't do that. You can put that on a whole bunch of supercomputers. It's better than doing nothing, but you're not going to get the best answer. And there's a lot of problems in artificial intelligence and machine learning that at their core, you have to search through a vast number of possibilities and find the best one in some metric. These are very difficult problems. And finally, the thing that got the field funded, factoring large numbers, it sounds like kind of a strange artificial problem. I want to take a big number and break it into the product of a couple of big primes. But it turns out that that scales not actually exponentially, sort of sub-exponentially, but super polynomially. And in 1994, it was shown that if somehow I could harness these, some exotic quantum phenomenon, instead of taking 1 billion years to factor big numbers on a supercomputer, I might be able to do it in seconds and break our current RSA encryption codes, the way that we send information back and forth. depends on the fact that it's hard to factor large numbers. What are those physical resources that are all around us, that are the basis of our reality, that we don't usually tap into for information processing? The first one, there's 4 basic ones. First one is quantum tunneling. You can have an object on one side of an impenetrable barrier, and it appears on the other side without passing through. Pretty weird, but this is, we make these devices every day. What it could allow computationally is I could explore solutions quantum mechanically that might be forbidden to me classically. The next one is energy level quantization. In an atom, you can have an electron that can exist at many different energies. They're not these classical orbits people think about. And the interesting thing is, you'll see in textbooks sometimes, you send some light in and the electron jumps from one to the other. But that's not what happens. You're not allowed in between. So you have to go from one energy level to the other energy level without traversing the intervening space. So that's pretty strange too. Happens all the time. Superposition, which you hear a lot about in connection with quantum computing. Classically, you think about a particle having a well-defined trajectory in space and time. But quantum mechanically, if you want to get the right answer for a lot of physical processes involving microscopic particles, they actually live out all possible trajectories simultaneously. So a single object can live out many possible histories. And this was the original idea, say David Deutsch, thinking about quantum computing. He said, what if I had a really hard problem and the same physical hardware behaved as if it was a lot of different hardware simultaneously, and each one of these trajectories was a different part of a very complex calculation. But I don't have to build a big data center. I have one processor that acts like a giant data center. So this allows for massive parallelism in computation. There's a caveat, but I'll get to that. And finally, entanglement, which really bothered Albert Einstein. This is when you can have two, what you think of as two objects. You measure something about one, and the other one immediately sort of has a perfect correlation with it. And I'll give you an example. This is just illustrative. Let's say I had a pair of dice. One's in California, one's in New York City. They're probabilistic events. We roll the dice at the same time 1,000 times. And classically, you would expect I get random numbers here, and they have nothing to do with each other. If these were quantum entangled, I would compare those lists, and 1,000 rolls out of 1,000 rolls the same. And this would be quite startling. And in fact, these experiments have been done, not with dice, but things like photons. And all of these are the phenomena that underlie the stability of matter, the structure of matter, radiation. Everything that we know is based on these kinds of strange things. But while they underlie how transistors work, we haven't actually used them in information processing. And what if we did? That's what quantum computing is about. I'll give you a simple example of something called a quantum gate, because we're going to talk about this a little bit. So most of the people in this room, you know that when you build complex electronics, I'll have some simple functions. Let's take the simplest one called a NOT gate. You put a binary 0 in, you get a 1. You put a 1 in, you get a 0. It's a simple function. There's a class of simple functions like and, or, not, nor. You put them together in complex arrangements, and you can build arbitrary logic and all the great stuff that our computers do today. Okay? Quantum mechanical version of that, you can encode information on a lot of different physical systems. It could be a transistor. It used to be, gear wheels and mechanical calculators, or an abacus. And what people first started looking at was, as I miniaturize these transistors, can I use individual atoms and molecules as computing elements? This is how it started. So if I have an atom, there's the proton and electron energy levels. I could call the first orbital a 0. And I could call the second energy level a 1. And we know that if we send in light of the right frequency, I can make a transition from here to here. So sending a pulse of light into an atom that was in the ground state and going to the first excited state means I started with a 1, I did an operation, I started with a 0, I got a 1. That's a NOT gate. It also turns out that if you're in the excited state and you send in a photon, you'll get stimulated emission. The electron will drop back down to that other state. A 1 becomes a 0. That's a NOT gate. So I've implemented a NOT gate with an atom, okay, just by shining light on it. But here's the interesting part. there's a time associated with this thing to go from here to here. The electron can't be in between. What it actually does is when you shine that light on the atom, you can think about the electron being here in the 0 state, and as that light turns on, it sort of fades out of existence. It fades up here, and now it's a 1. Leave the light on again, it fades back to a 0. So if you leave the light on for half the time it takes to make that transition, it's in both places at once. That's a quantum gate. It's called a Hadamard gate. You put a 0 in, and basically the way you'd implement this is I have the atom, I start it there, I shine it for half the time it takes to make a transition, and what comes out is this thing in this weird state of being a 0 and 1 at the same time, which is a quantum bit or a qubit, okay? And so what people who think about this sort of gate-like model for quantum computing now, in ion traps, this is a cartoon, imagine you had a whole bunch of atoms like that. And now for each atom I have a laser, so I can excite it. I can have that electron in the ground state. I can build a register out of this. I shine light on an atom for half the time it takes to make a transition, and I put it in this strange state of being a 0 and 1 at the same time. And I do that for every one of them. So here's where you start getting an idea of the power of quantum computing as traditionally thought about. Now, this single register that has 8 bits, in a classical register where I had transistors that were either 0 or 1, I could have 2 to the 8th different possibilities for that register, okay? But at any given snapshot in time, I only have one of these. In this quantum register, by just shining that light for half the time for each of those, it will be in a state that encodes all of those registers simultaneously. It's all 0s, it's all 1s, it's every combination simultaneously, okay? Now imagine you made a 300-bit register, and you can see what happens. Every time you add a qubit, you get a factor of 2. So the number of possibilities grows exponentially. So if I had a 300-bit register, I would have 2 to the 300 possible combinations stored in a single register simultaneously. And that's more numbers than there are particles in the universe. These are the kind of things you hear. This is the exciting part. Now the question is, how do I take that information, process it, and get answers out? It's not as simple as I have this parallelism and I have 2 to the 300 answers at the end. Because there's another thing about quantum mechanics. When I look at that register, I'm going to see one of those. So you have to find a way before you do a final measurement to have those different threads, those histories, kind of interfere with each other in such a way that I get the cumulative answer. I've actually gotten the advantage of all those paths, but I get a single answer at the output. That's the hard part of writing quantum algorithms. Okay, so people started trying to build these things. And there's a whole bunch of different physical platforms you could do that with. There's people doing it with photons, microscopic particles of light, optical lattices. This is an example of an ion trap. You have the atoms are in there, floating in these electromagnetic fields, interacting through lasers. I can have interactions between these things to create logic. One of the problems with these approaches, if you wanted to scale up, is these are microscopic objects, atoms, photons, right? How do I build a control system to control microscopic elements and then scale it up? Nobody knows how to do that right now, and it could take a long time to build technologies that were capable of doing that. Now, something interesting is that this is a D wave chip, and this is very macroscopic by comparison. There's a misnomer about quantum mechanics. That quantum mechanics, and I hear this on a lot of journalists say this, a lot of quantum computing people say this, so I'll dispel it right now. Quantum mechanics is not the physics of the very small. Quantum mechanics is the physics of everything. So you have this problem. If microscopic particles are in many places at once, living out lots of histories at once, and going from place to place without the intervening space and all that, and we're built out of them, why don't we do that? We know why now. We know how the classical world emerges from all of that quantum weirdness. And I'm going to give you a hand-wavy argument, not a technical argument, but way back when, here's the Schrödinger equation. And what it predicts is microscopic and macroscopic alike. I should be in these strange states. Here's a cat alive and dead at the same time. Why don't we ever see that? In the 80s, there was a new field or a new discipline. It talked about something called decoherence. And here's the thing. If you look at an electron or a photon, an electron doesn't interact with its environment very much. An electron passing through this room will scarcely bump into another air molecule or photon. But a macroscopic object, like a cat or any of you, is constantly being bombarded by air molecules, by radiation fields, and it turns out that if you take all the interactions into account of an object with its surroundings, and you put it into this equation, you'll find that what emerges is classical-like states. And I'm going to say this in kind of a funny way. What happens is, if you have quantum weirdness here, so let's say all of those weird effects are in this region of space. When a particle comes in, some of that weirdness gets passed out. It doesn't disappear. This idea about the collapse of the wave function, there's no evidence for. What we do have evidence for is that the weirdness gets passed out to all these other degrees of freedom, particles, radiation fields, that cat standing on a floor that's vibrating. And when you take all that into account, you can see how the classical world emerges right out of quantum mechanics. Now this, another way to think about it is energy conservation. If I drop a tennis ball from here, why doesn't it come up to where it was? Because the energy went away? No, it went into vibrations in the floor and sound waves and all that. So it gets passed out to other things. So this allows for an incredible possibility. If I could put this cat in an ultra-high vacuum, get rid of all the air molecules bounding into it, if I could shield it from all the radiation, if I could put it on a floor that's really, really cold so there's no vibrating atoms, the weirdness doesn't get passed out. Now, in the case of the cat, there's another issue, is that even internally, the wiggling of its own atoms will get rid of the weirdness. But the interesting thing is, the question since 1935 is, can you build macroscopic quantum objects? Answer, yes. In 2000, this happened. It was in the New York Times. Schrödinger's cat lives. And it was in a really interesting object. This is a superconducting ring, so a ring of niobium metal, could be aluminum. Unlike the cat, when you go to very low temperature, electrons can go around this ring without bumping into anything. And they can go around forever, non-dissipatively. So the weirdness doesn't get passed out inside the ring. And then the idea was, what if I put this ring in a rarefied environment of ultra-high vacuum, ultra-low temperature, radiation shielded, all of that stuff? And when you do, you can put this into this really exotic state wherein I can have a current that goes around this ring, all the current goes clockwise, and all the current goes counterclockwise. And now I have something that can encode a 0, current goes one way, and a magnetic field up. Current goes the other way, magnetic field down. I have a qubit in a macroscopic object. And what that allows for in quantum computing is that I can build macroscopic qubits that I can couple to macroscopic control elements. I can engineer them, unlike atoms and molecules. And there's already existing technologies for superconducting logic where I can interact with these strange quantum objects, with other quantum electronics, and maybe build things at scale sooner rather than later. Okay, so now we have the story. It's like, now you have to build an organization that can pull this off. When we were thinking about putting D WAVE together to really do this, you can't do this with a lot of disparate efforts. We took as our model something like the Manhattan Project or, say, Celera Genomics. You have to have an interdisciplinary group where you have physicists, engineers, material scientists, computer scientists, all working together. You have to have specificity of purpose. You have to have an interdisciplinary team. They all have to be together, working together every day. This is very important, rapid prototyping. The only reason these programs succeeded on very short timescales is you have to iterate over and over. These systems are too complicated to model from first principles. You have to build them, you have to test them, you have to learn, and you have to do it fast. The other thing is you have to leverage the best existing resources. So we took superconductivity to the semiconductor industry and very quickly used the $1 trillion they've spent over the last 50 years to make the best superconducting process in the world. You don't want to reinvent the wheel. And of course, there's a lot of leadership, and oftentimes in technical efforts, this is vastly underappreciated, the coordination of the effort and all of that project management stuff. So we did this at D WAVE. That's a picture of our new building. You can see banks of dilution refrigerators. Under this roof, we have theorists, experimentalists, design teams, electrical engineers, applications, everything under one roof. And a rapid prototyping with lots of fridges, lots of, we can do material science, fabrication, state-of-the-art, and that's our mini Manhattan project. Just a quick overview, we have about 100 employees. We've raised about $130 million in capital from some really great investors, lots of US patents, maybe more than all other companies combined. And we do publish a lot. If you want to read about what we've done, how we've done it, about 60 peer-reviewed papers. And most recently, we have some fantastic partners with you guys in Lockheed Martin and USC. Okay. The other thing about our approach was we had an evolutionary approach to building quantum computers. The idea was, there's this dream machine that could do in seconds what might take billions of years, but how do you get there from here? So if you keep working on that perfect computer and it's taking you forever to get just a few qubits, you might lose interest. So what we looked at was, is there a model of quantum computing, adiabatic or quantum annealing, that could a special purpose quantum computer that could solve high value problems, prove that this technology has legs, and give you a chance to move forward and sustain investment. The other thing to understand is that some of these theoretical constructs don't say much about the real world. So this polynomial versus exponential scaling, I'll give you an example of that. In the real world, there aren't an infinite number of planes to figure out how to schedule at Delta Airlines. Real problems are bounded, right? Maybe I have 500 airplanes. So it'd be nice to get polynomial scaling, like in the Shor algorithm, versus exponential. But if you get a better exponential, where it's 2 to the n over 10, that's worth billions of dollars, and it has huge impacts on all kinds of industries, including what you do here. So it's important to understand real-world problems versus theoretical constructs when you do this. Now, there's different models of quantum computing. Which one would you choose? So there's something called the gate model. I just showed you a little example of a quantum gate. Some of the issues with the quantum gate model is, I'm shining that light on that atom, or I have to shine microwaves on superconducting circuits. There's a lot of high-frequency engineering involved. It's very sensitive to noise. And so it's been really hard for people to build systems because they've had to spend years and years figuring out how to get rid of all those interactions with the environment so that you could do anything practical, even at the few qubit level. There's another model. I'm not going to go into topological because it's based on objects we don't quite know exist. But adiabatic quantum computing is another kind of computing that offers the advantages that it's a lot less sensitive to noise. So you could start building things at scale sooner rather than later. It doesn't have the really stringent noise requirements or very low noise requirements as the gate model. It's something that uses low frequency control and not a lot of high frequency lines, which is hard to do even in classical circuits. And we chose, obviously, superconducting materials so that we can engineer things with existing technology rather than trying to build whole new technologies for microscopic constituents. Okay, and if you look at kind of the current state of the art, the two big models anyway, in the gate model, there's Shor's algorithm, quantum gates, there's analogs of classical gates in the quantum regime. There's a well-understood theory and about how you can correct errors. Kind of state of the art in terms of numbers of qubits, you can see there. That's because it's been really hard over the last 20 years to get the requirements to where they need to be for that model. Empirical scaling, there is no data because the systems aren't big enough yet. And this is just, this is not, this is just an estimate. A lot of people are looking at the gate model to factor numbers. So if you wanted to factor a 768-bit number, which was kind of a record, and you used a certain kind of error correction, of course these things could change, where you're using 1,000 physical qubits for one logical qubit. You'd use redundancy to do error correction. And you start from these numbers and you double the number of qubits every 18 months, like Moore's law. It could take you quite a long time to scale to do Shor's algorithm. So it's a major undertaking, a major effort. But tremendous progress has been made and amazing science, and I'll talk a little bit about that. In quantum annealing, this is, I'll describe. There's less known about it theoretically. There's some experiments people have done where you could get an advantage from doing things this way. It's much easier to scale. We're now exploring the scaling. And maybe we could beat everything in a few years based on where we're at now. And I'll talk about that. So quantum annealing. So rather than turning calculations into a series of gates and doing mathematical calculations, this is a little bit like doing analog computing. I'm going to use the physical evolution of a physical system to solve problems for me. It used to be that people would build an electrical circuit, and the physics that governed that electrical circuit would solve differential equations. So there's a theorem in quantum mechanics called the adiabatic theorem. But I'll start off with this. So let's look at imagine that this is a rubber sheet, and I put a little ball there, okay? And annealing actually comes from, people used to do this with metals, right? I heat up a metal to a very high temperature to let its atoms move around, and then I cool it slowly, and maybe they can find the best positions, the lowest energy configuration, and I get a stronger sword. What people did is they said, nature seems to look for these low energy solutions. There's a lot of problems where I'm trying to find some minimum of some complex function of interacting parts. Maybe I can write code that simulates this physical dynamics, and that was called simulated annealing. And what they do is you have some physical system. I'll talk about what kind in a minute. And you put it in this very simple energy landscape, so things are going to roll to the bottom. And then I gradually deform this rubber sheet. And what I'd like is, as I deform it, and it gets more and more complex, and you could have millions of hills and valleys, what I'm looking for is the lowest valley. And the problem here you can see when people write simulation codes or when they actually do this with real physical systems, in classical systems, you tend to get stuck in what they call local minimum, and it's not the best answer. I'd like to be there. And of course, for real problems with lots of variables, you could have an energy landscape with a horrendous number of hills and valleys. Quantum annealing is based on this idea that if this object or this system is quantum mechanical, it isn't a little ball that's in a particular place in this energy landscape. Under the right conditions, I can turn on quantum tunneling, where I talked about things ending up on the other side of barriers they can't pass through. It also can be in many places at once. And so instead of having somebody looking through this vast energy landscape by running around from one point to the next, I could span the entire landscape. I could tunnel through these mountains and kind of ooze into that lowest energy state. And if I could do that for large-scale problems, I can encode problems of interest to people into this kind of schemata and solve some really high-value problems. I'll talk about what that is. So as an example, here's like a traveling salesman problem. I'm a salesman. I want to go to a whole bunch of different cities. This is a pretty famous problem. How do I go to every city at least once, come back to where I started, and the minimum distance? Okay? This can be recast as finding that energy surface represents all the different paths. So instead of energy, each point on that landscape represents the path length, and I want to find the minimum path length. And there's lots of them. And this scales exponentially with the number of cities. One thing I'm going to mention here is in this adiabatic evolution, this is where the system starts out in that very simple well, and then these are all the other higher value solutions. And then as you evolve this system, you end up here. That's the shortest path, the next shortest, the next shortest. Another thing about real world versus theoretical is people tend to talk about the global minimum. But in the real world, if I can do better than anybody else can, let's say this represents finding the lowest path here, or this could be the FedEx schedule. If I find a better schedule than anybody else in the world, even one of these low-lying solutions, that's worth a lot. Okay, so what physical system, this is a classic physical system people have thought about to do this sort of adiabatic evolution. And it's called an Ising spin system. So imagine that you had a bunch of little magnets or quantum spins. And each magnet, so I have a magnet here. Each magnet I can put a little horseshoe over, and it's going to tend to orient north to south, right? So I can bias that magnet up or down. So each magnet has a little local field that can act on it. And then the magnets have interactions between them. So I can have the magnets interact so that they want to be the same way, so the norths are both up. I call that a ferromagnetic. Or I can have the interaction such that they want to be the opposite direction. And I can control the magnitude of the local field that makes it to want to be up or down a little bit more, and I can control the interactions between them. Well, it turns out that if you make an array of such magnets, and I can tune all the interactions between them, and then the local fields acting on them, and then you ask the following question. For those local fields, and for those interactions between the magnets, how will the magnets arrange themselves to minimize the energy of this system? That turns out to be a horrendous problem, and the solution to that scales exponentially with the number of magnets. And how hard the problems are depend on the details, like the interactions and the local fields. But the interesting thing about this is people have thought about this problem for a long time. Ising spin network. You can see this formula here. Basically, you have each spin. It has its local interaction, and then interactions between the spins, this J, between neighboring spins. And then the next part of this equation is, OK, this defines a problem. So for a given local field and interaction, what's the lowest energy? But how do I find that energy? I can either jump around that landscape, like in the classical case, and try to find it, or what this represents is a tunneling energy. We actually have a knob on our physical system where we can turn on quantum mechanics. We can turn on tunneling so that it can cut through these mountains and valleys and try to ooze into that lowest energy solution. And if you can do that, maybe you find better solutions than anyone classically. And if you could solve this problem, solving it's equivalent to a lot of other hard, very high value problems. And some of them, say at Google, include things like optimization that you do in machine learning and AI, and protein folding, things like that. So there's a whole range of applications where if you could solve that effectively for a large number of variables, the trick is we have a whole group at D WAVE, and you have people here who figure out how to translate the hard part of important problems into that formalism. And these are some of the areas: pattern recognition, protein folding, finding information in big data sets, bioinformatics. And this was just a quote by someone you know and love, Hartmut. But he introduced us to the possibility of using these kinds of resources for doing machine learning. And this is sort of maybe the future of looking at big data and getting useful insights. And people agree. So, OK. So now how do we build this thing? So we're not using little electron spins. This represents electrons they're not really spinning, but it's as if they're spinning and they have a little magnetic moment. OK? And for a real spin, you can put a magnetic field. These are like poles of a horseshoe magnet. And I can try to orient it up or down. And I can do that for every magnet. And then they can have an interaction between them. But of course, real electron spins are microscopic, and it would be really hard to build a technology based on these. So I just told you that I can build an artificial spin. I can have a superconducting ring that's very macroscopic. I can run a current around it, and that current going around will create a magnetic field up or a magnetic field down. Okay? You'll see two control elements. I can put magnetic field into the body of the main loop, and that will act like this horseshoe magnet, making that thing want to be up or down a little bit. Okay? So I have a control for that. I have a second loop with a couple of things called Josephson junctions. I can put a current in, and that will act like a transverse field, like a field perpendicular to these spins. And what a transverse field does on a spin is it can put it into a state where it's up and down at the same time. So when you put a transverse field on a spin, it turns on quantum mechanics and allows that spin to tunnel between states, or to be in two states at once. So we have the local field here, and this is how we turn on quantum mechanics in our loops, where we have an effective transverse field. Okay? You put these spins together in an array. This is them realized on a chip, and you say, where are the circles? I'll tell you about that in a second. And interesting, it also looks rather like a neural net. You have objects that are connected to other objects that have interactions. And so rather like a neural net structure, and maybe good for learning. The actual qubits here, when you actually build real circuits, you don't just have circles like that anymore. You'll see these sort of horizontal lines, vertical lines. They're long, skinny qubit loops. Currents go one way, you get a 0. The other way, they get a 1. When you put flux in that one knob, they can be in both states simultaneously. Most of this chip is the control circuitry to do all of that. And this is where you get to the hard part. You can build a few qubits, and you can do some really great science, but now you want to scale it up. So when you build real objects, they're not identical. Electrons are identical to each other. Photons are identical. But even so, when you build control systems for those, the control systems won't be identical. So you're going to run into this no matter what you do. So in a real manufacturing process, this qubit is not going to be exactly like its neighbor. So what do you do about that? I want to have these uniform properties for these macroscopic engineered qubits. And we figured out how to do that. It took years, but it's been successful. Each qubit has a whole bunch of in situ tunable characteristics where I can put flux, again, this is like a little inductor. I can run current, it puts a magnetic field in a loop, and just by putting magnetic field in a whole bunch of loops around that qubit, I can tune out all of their differences and make engineered qubits essentially identical, like electron spins, okay? Now, to do that, now you run into something else. You'll notice that for each one of these, I've got a couple of wires here, I've got a couple of wires here, I've got wires here. If you add the number of wires going to this qubit, say it has 5 or 6 control elements, and you say, okay, there's 12 wires in and out, and I want 1,000 qubits. Now I have 12,000 wires. You're not going to put 12,000 wires around a chip, right? Even Intel doesn't do that. So what do? Now I have to have a routing system that somehow gets these flux into each one of these loops to tune out these variances in my qubits. And it turns out that when I was at TRW, there's a mature digital superconducting circuit technology called single flux quantum logic. It operates at the same temperature you need to run these qubits at. It sends chunks of magnetic field around with no dissipation. So it's not going to take the weirdness away. And you can interact with these circuits at scale with kind of a flux router. And so when you end up with a chip like this, you can see here, I've drawn a schematic. You have these long, skinny loops. There's a qubit. There's 4 horizontal qubits, 4 vertical. This is our unit cell, the basic building block of our quantum processor. Here you can see it here. You can hear it here, and right where they cross over, they interact with each other. And then, of course, they interact with the next unit cell over there. And you can see that most of what's in this circuit is control circuitry to get flux into all those loops. We have to first take out all the variability in all the qubits. Then we have to be able to put all the local fields and the interactions between them to define a problem. And then I have to put flux into that loop that turns quantum mechanics on to have it tunnel around and explore the landscape. And then after the evolution is done, and hopefully it's in the lowest energy state, I have to read out all the qubits to see how many spins are up or down, and that's the answer to my minimization problem. Okay? There's an actual chip. This is a 512 qubit chip. You can see each square is one of those unit cells. This is a lot of test circuitry you have to put on there. Lots of bond wires. Now I have to take this. How do you build something like this? This takes a world-class fabrication facility. So we took superconductivity out of the R&D labs, and we took it to a real production fab. If you've never seen one, they're really impressive. This is Cypress Semiconductor in Minnesota, top view. This just shows some of the circuitry on chip, just one layer out of many. And these are rooms and rooms and rooms and football fields worth of $10, $20, $50 million pieces of equipment to be able to build things at scale. And we have the most advanced superconducting circuit processor. Now, remember what I said. For macroscopic objects, the reason they don't normally show themselves in these weird ways is because they're interacting strongly with the environment. So the first thing you got to do is you put the chip in a protective environment, the right kind of materials. All these lines are superconducting, so there's no heat, no dissipation. We put a cap on top of that, radiation shield. Of course, I have to send signals down to control the chip and its evolution and read it out. But that's coming from room temperature, so it has little wiggles on it that could cause the quantum resources to get passed out. So I have all kinds of complex filtering for all the lines, so only the signals I want and not what I don't want. Lots and lots of layers of shielding. And then that whole thing, it's like, okay, that's enough. So maybe I've shielded some magnetic fields out and I pull a vacuum on it, but that's not enough. I have to go to very, very low temperatures, even lower than necessary for superconductivity, because the chip sits on a surface whose atoms are wiggling. And again, you could pass out the weirdness to those wiggling atoms. So we take the chip down to a temperature that's 100 times colder than interstellar space, at 20 millikelvin. And now you can see the whole thing buttoned up, all these highly filtered lines. And again, guess what you get to do? Some more shielding. And you want to make sure that the electrical signals in here aren't hot, so you might do optical isolation. In addition to which, if there's ambient fields, the Earth's magnetic field, which is quite weak, we've developed a method using quantum devices called quantum interference devices to measure the magnetic field in 3 dimensions, create canceling fields, and getting the field that this thing sees to 50,000 times less than the Earth's magnetic field. All of these were innovations we had to do really fast, and they all work, and there you go. Now this, you can see that this is the actual system all buttoned up, but it's in a big box. There's the big box. What's out here is, you know, what sends the control circuitry in, the pumps to keep the thing cold, and the big box itself is, you know, stainless steel and copper, all that to keep radiation and radio waves and all that stuff from the outside world, again, to isolate, to have those robust quantum effects taking place. Now, I often get asked, why is this 10 by 10 by 15? Is it because the thing's that big, like the old supercomputers with banks and banks of relays? No, it's so 4 physicists can fit inside. As we go, eventually this, you know, maybe could be a 19-inch rack, the actual dilution refrigerator, something like that. And this is, you often have people inside working on things, so, you know, it's more convenient in the short term. This is the one at NASA Ames that got installed that you guys are using. And a lot. I'm really gratified about how much use this is getting, and the uptimes have been fantastic, something like 99% or 100%. And another box here at the USC ISI. There's Daniel Ladar and Dean York Post. So cool stuff. And lots of results coming out of both labs. Okay, something about quantumness. So often it's asked, how quantum is this thing? So every experiment done to date has been consistent with quantum dynamical models. So when you want to look at quantum effects in a processor, right, you write down the equations for those rings and their interactions and all that. You put it through that Schrödinger equation. You also add a little bit of environment because it's not perfect, and you get results. And then you compare experiment to those results. What we've typically done is we've taken in a processor, domains in that processor, and checked them for these quantum mechanical properties. And every time we do that, they meet all the quantum dynamical equations and not classical. This is an example from our Nature paper. I don't have to go into it, but that's the quantum predictions, that's the classical predictions, and everything lies on that for an 8-qubit unit cell. Recently, we looked at entanglement in an 8-qubit unit cell, which is, I believe, the largest solid-state demonstration of entanglement ever done. And again, we see that. Now, the question is, if we look at it at a lot of different unit cells and domains within a large processor, what about entanglement over 500 qubits? So I'll tell you, this is going to be a challenge for everyone in the field. Nobody can write down the equations for 512 qubits and write down what the answer that you should get. And even if you could do that, the number of experiments you would have to do to confirm that is something like 2 to the 2 to the n, where n's the number of qubits. You can't do enough measurements to fully characterize the quantum state of very large systems. Everyone's going to run into this. So what people are looking for is, can we see signatures of quantum effects in these larger scale processors? And at the end of the day, is it beating everything on Earth for some set of applications? And that'll be that. But this is going to be true for everybody. Okay, and lots of good results also coming out of USC, one of which they're looking at error correction now. Some good stuff from all of our partners. Now I'm going to talk a little bit about where are we at with this processor. We're at a scale where we can start playing with it, you guys are, to see what it does. Again, I'll remind you, basically what we do is we have some function of a string of binary variables. So some function, it could be some complex function you guys use in machine learning, and it's a function of 512 zeros and ones. And I want to find what set of zeros and ones minimize that. Okay? It could be an error function when you're training a neural net. And I turn that problem into, you put a local bias on a spin, I have interactions between the spins. Now I turn on my quantum tunneling term so it can explore that complex landscape and hopefully ooze into the right answer. And at the end of that, I should have a bit string, up and down of all those, that I can put into that, and I'll get a very low value, lower than I can do any other way. That's the idea. Interestingly, just from the cool quantum magic side of it, at the very beginning of this, when you turn on that tunneling term, that array of magnets is in a superposition of all possible permutations of that lattice. So what that means is all the spins are up, and they're all down, and half are up and half are down, and they alternate up and up, down, you know, and there's 2 to the 500th permutations, and they all exist simultaneously, which is kind of mind-bending. Okay, and again, just reminding you, so there's the spins, 4 horizontal, 4 vertical, they interact, they're like little magnets. I put a horseshoe on each one to kind of make them want to go up or down, and if that's all what's going on, it's easy. They're all going to line up, you know, north to south. But now you add some interactions where they want to be like some of their neighbors or unlike other neighbors, and it becomes what's called a frustrated system. If you're interacting with a whole bunch of your neighbors and they're all telling you different stuff, what do I do? And the same thing is happening to all of them, wherein you get this incredible complexity. Right? Lots of variables interacting. How do you satisfy all of those conditions simultaneously, maximally? Okay? And this just shows you, here's the problem. So this represents the problem. You kind of introduce the problem, you know, these fields and couplings. And this represents turning on that tunneling term where it spans the whole space. I'm not going to go into the details, but the bottom line is you start off where it's everywhere at once, and there's not much of a problem. It's everywhere. And gradually, this is where it's oozing around in the landscape, and the problem starts making itself known. And at the end, you're not tunneling around anymore. You're in the bottom. You're not everywhere at once. You're in the solution. Okay? So question is, when you do this, now keep in mind, this is a first-generation processor. There's a lot of imperfections with it. You know, it's sort of hot off the press for a few months, and you say, okay, let's compare it to some off-the-shelf solvers that solve these kinds of optimization problems where they try to find the best solution amongst a large set. Okay, so we took a single-core Intel Xenon, and there were these 3 different kinds of methods for searching through those complex energy landscapes. And we ran these, and you guys ran these. The result was really encouraging, right? So when we first saw this, this represents, without going into all the details, this is kind of the time to solution and how it scales with the number of variables. So it's this how does it scale thing. And also, the point here is the absolute time to solution, say at 509 qubits. So what was remarkable is that this first processor, we saw, say, with some of these commercial solvers, something like 35,000 times faster to the best solution on our little 500 qubit chip, right? Now, if that was the end of the story and it did that for everything, we'd be done. And we'd be, you know, everyone would want one. But the reality is these are general purpose solvers, and ours is this special hardware designed for this. So if you did a lot of iterations, even with these existing solvers, maybe that 35,000 comes down to 100 or a couple hundred. Still really impressive, because people spend a lot of money for a factor of 2. But this is really encouraging. So what this tells me is we've built a real computer. We know that it has quantum dynamics going on in it. It's finding the best solution out of 2 to the 500 states. This is a highly non-trivial calculation, right, in just a few years. And the hardware that it's going up to is incredibly impressive. You know, if you look at that processor, the Intel processor, that's 50 years of development and $1 trillion. Okay, but then there were some other tests everybody's aware of. So some good people got together, Matthias Treuer and some guys, Martinez at UC Santa Barbara, and you guys, And the idea was, all right, let's take the best special purpose classical processors and algorithms and see if we can do better and go head-to-head with this D-wave optimization machine. And so again, we're solving this problem of having spins with a local field and interactions between them. There was a problem set chosen where the interactions were kind of random and all the way on or off to make it simpler. The competition, and just pointing this out, the way this works is it doesn't see all the solutions simultaneously, quantum mechanically thing. Instead, you have a spin lattice, and it will turn spins over and look at the energy, kind of. And it'll keep doing that really fast. And every time it turns spins over, it kind of looks at the energy and keeps moving those spins around until it comes to the best solution. So interestingly, if you look at something like this Intel Xenon, it's about 5 billion flip evaluations per second. Pretty amazing, right? So these are very powerful chips. These GPUs actually are in the Titan supercomputer. OK. And so an experiment was done by this group. Ran hundreds of millions of experiments on the D WAVE processor, which is nice because it's working robustly, even though it's early stage, and billions of simulations in classical and quantum Monte Carlo code. OK, so preliminary results. What this shows you, again, is sort of the time to solution. This is kind of a median time to solution, averaged over a lot of problems, as a function of problem size. And what you see here, the blue lines are the D WAVE machine. And you see the other lines that are various forms of using these highly optimized classical solvers. And you'll see here, here obviously we're doing much better. There's kind of a generic solver, which is something called a metropolis algorithm that's flipping these spins, subject to a special algorithm that's like simulated annealing, doing this classical search of those energy spaces. We do better, say, in terms of the time to solution. And then you can see that highly optimized, this is playing with how you actually use that processor, knowing the details of its operation. Then you can get highly parallelized things. You take a couple of CPUs, or 8 CPUs, I think it was, in parallel, so you can parallelize some of these operations. And you can see, OK, it's competitive with what the D WAVE thing is doing. And then if you take GPUs with these 2,600 cores or something, I can exceed that for some set of benchmarks. Now, more importantly, what people look at is they say, well, I don't care so much about the absolute time. I'm sure D WAVE, there's engineering overheads. How long does it take to program the problem, read out the problem every time we come out with a new version that gets faster? What people tend to look at is the scaling, like I said before, in complexity. So if you get a smaller slope, say with some quantum processor, and you extrapolate out to 10,000 variables, then it's game changing, right, for a whole range of applications that you could port to this. Now, what we know is that this scaling is not fundamental to the physics of our device. So what's very useful about these studies is, OK, let's take the best stuff out there, and let's learn what is it about our processor that enhances performance and what robs performance. We know right now that most of the problem is misspecifying the problem. So the problem is putting the local fields and the interactions between our qubits, and they're off, right? We have some systematic errors I'll talk about quickly. And we also have some noise. And so we expect that the scaling will get worse as you get bigger because these errors accumulate. So there's no evidence that fundamental physics is limiting it. We also found that the random problems that were used to do this benchmarking intrinsically shouldn't be that hard. So if you look at these energy landscapes, when you have lots of these big valleys and there's lots of ways to get to them, even if you're a little ball rolling around, there's lots of these deep valleys you can fall into, actually lots of ground states that are sort of equivalent, or paths to them. So there was Professor Katzgraber, papers on the archive, about how these kinds of problems with the kind of structure we have in our processor shouldn't be that intrinsically hard for classical solvers because those energy landscapes lend themselves to classical solutions. Okay? So this was interesting, and this was learned kind of by doing this. We also ran other kinds of problems where we tried to engineer the landscapes so that those deep valleys are surrounded by mountains, sort of. And then we find different scaling, right, where we look much better in those cases where tunneling should be important, right? Now, these are all preliminary results, but what's exciting is we're starting to learn what limits our processor, how to make it more powerful, and we're showing after just a few years, instead of 50 years and $1 trillion and all millions of man-hours of algorithm development, where we're matching kind of state-of-the-art stuff. And this is really exciting. And the scaling will only get better with improvements. Some evidence to that fact is we have these different generations of processors. And every generation, we improve the precision to which we can specify our problems. So here's 2 generations, V5 for Vesuvius. We name our processors after mountains. And you can see the scaling, the median time to solution for V5. We made some improvements on V6, and you can see the scaling starts getting better. And we expect as we go to V7 and Washington and future generations, as we increase precision and reduce noise and all the factors that could impact performance, it should just get better and better. Another thing, too, is the pace of discovery that's going on. We have our 128-qubit generation. When we went from there to Vesuvius, typically in a cycle of a couple of years, people go for a factor of 2, say Moore's law. We got a factor of 300,000 speed up from one generation to the next, and it was a complete architectural change. We don't just expand the number of qubits. We looked at everything that affects performance, programming it, reading it out, the size of the qubits, energy scales, anything that might affect quantum dynamics, and we've got this kind of speed up in a couple of years. So really encouraging in terms of the pace of discovery. So next steps. We know now the things that are limiting our performance on these current generation of processors. We know that we need to increase precision. You have to define the right problem. We might be getting the right answer to the wrong problem, and that skews the scaling. We also know that we need to reduce noise. We also know that we have to increase something called our qubit energy scales. The bigger the energy scales of the qubits, the less fluctuations play havoc with them. Reducing the temperature, I'll talk about that. The other thing is to make this thing easier to program. Right now, each qubit's just connected to 6 of its neighbors, right? That's not that complex. If I'm a variable, and I want to connect to 20 others, I have to use some kind of complicated embedding for me to connect to you. I have to use a lot of intermediary qubits. So we know that both to increase the complexity of the problems we can instantiate and to make them much easier to program, we want to increase the connectivity. We also were band limited on how fast we could do this search process with quantum tunneling. We're going to be speeding that up. And in addition to all of that, we're scaling up. So I'll give you an idea of the kinds of things that limit precision when you build large-scale circuits. Remember I told you that we put magnetic field into these little loops, both to control the whole quantum computing process and also to calibrate all these things and take out their variances. When you put magnetic field into one, sometimes it'll spill over into another, right? Why? Because when you look at what these processors actually look like at scale, it's, you can see here lots and lots of layers, currents running down, magnetic fields. It took years to build programs, to do 3D modeling, lots and lots of generations to figure out how to shield and isolate just to get where magnetic fields where you want and not anywhere else. So real quantum circuits are going to be very complex, and it's going to require lots of engineering and resources and iterations. We're making our ability to put flux in those things more precise. The flux goes in little units, and we're making those units smaller by changing our digital to analog converters in our superconducting circuitry. We had some knobs. This was the knob on our coupler. On the previous generation that you guys still have, when you turn a knob, a little turn in the knob and you get a big change in the outcome, that makes it difficult. If you have a light switch, you turn it a little bit and the light turns on a lot, it's hard to control. In another version that we built and confirmed, we now have a flatter response in that coupling, so it makes it that much easier to set the couplings correctly. Additionally, this is one, we found one of our biggest problems in specifying problems. When you have a real physical spin, and I put a magnetic field on it, it doesn't change the value of the spin. But we don't have real spins, we have artificial spins. So when I put a flux in this loop that acts like a magnetic field, this loop will generate a little current to kind of push that field back out. And when it does, that means it changed the value of the spin, and it also percolates out through its couplers to its nearest neighbors. So we call this magnetic susceptibility. You put a magnetic field on, it reacts a little. We now have a design to cancel that out completely, and that'll have a big impact on precision. I mentioned this, energy scales, smaller qubits. You want big energies compared to thermal fluctuations and noise. We can make bigger energy scales by smaller qubits and smaller junctions. And we're already building the next generation that includes those. Another thing is temperature. At the end of your evolution, here's all the energies. So remember, each one of these energies represents a different configuration of that spin lattice. Okay? That's the lowest energy one. But we operate at 20 millikelvin, and as cold as that is, you still have some thermal energy to knock you into these higher lying states. And the extent to which you're knocked into these higher lying states depends exponentially on temperature. So small changes in temperature give you a big bang, give you a lot more probability to be in the low lying states. So we're going to be going from 17 millikelvin to 10, which should give us a big boost. And that's in the shorter term, which we think we can do reasonably soon, and eventually go to 5 millikelvin, and we should get a dramatic increase in the ground state probability and the lower lying answers, better answers. Noise. So we've been asked this a lot. So I've often heard the comment that D-Wave doesn't care about noise. They want to put a lot of noisy qubits together and see what happens. This is not true. Here's the philosophy. So people working on the gate model, even to get started, they have to have very low noise, even to build few qubit systems that can do anything. Because they operate in this regime where they're using multiple, higher lying energy states and interactions between them. When you have a bunch of energy levels, everything always wants to go to the ground state, the lowest energy state. So it's thermodynamically unstable. You're doing non-equilibrium computing. You're driving things with microwaves or light waves. In the adiabatic approach, you always want to stay in the ground state. You're in the ground state, you evolve that landscape, and you want the ground state to evolve with it. So the dynamics are slow, and you tend to relax to the state you want to be in anyway. It's kind of natural error correction. And so it's thermodynamically more stable against this. So you don't need to have these unprecedented low noise levels to get started in the adiabatic process. So the decision we made was everybody in the world is working on low noise, right? We don't need to. We can get started. But what nobody's working on, because they can't yet, is figuring out how to build large-scale circuits to control all their stuff. So let's do that. It's complementary to their effort. And in about in the last 10 years, with about 500 man-years worth of materials development, they've had an improvement by a factor of 1,000. So now that we have a working processor, and because it's less sensitive to noise, and we have quantum dynamical things, and we're doing real calculations, we can leverage all the learning done and start incorporating in our processors to eventually get something like that. And it's not so exotic. What was discovered in terms of how to do this. You can't just plop it in. There's parametric changes, but we know where to go. And likewise, we've worked on these large-scale superconducting circuits that the rest of the community could leverage on our end because we've been developing that for the last 10 years. We do a lot of this work at JPL as well. Just want to say hey to them. And so where are we? We've built working quantum processors in a scalable architecture. Even early generations are showing promise, matching state-of-the-art processors for some problems, and on some problems exceeding them. We're starting to really understand what makes us powerful and Rob's performance, rapidly increasing our capabilities with each generation, developing real-world apps, and that helps us understand the architecture, connectivity, and techniques we need. It's fantastic that we have an ever-expanding group of brilliant people to think about how to use this, and obviously visionary partners. So stay tuned. We've been on this Moore's Law-like scaling for the better part of 9 or 10 years. We don't expect that to abate. And this is what's in the lab right now.
So since you are so rapidly developing the processor technology and everything else, is this more of a sales model or a lease? So is Google stuck on the old generation of the processor, or do we see the improvements from?
Oh yeah, of course.
Yeah. Okay.
Yeah, of course you will. Yeah. Yeah, obviously, you started with earlier generation processors. You learn how to use them. We understand, and from the user's end, we're getting a lot of insight into what you need. Whether it's connectivity or all that other stuff, right? Yeah.
It sounded like one of the main engineering challenges was making sure that these squid machines are all essentially functioning identically.
Yeah.
But I didn't understand why that's so important for the physical model.
Oh, well, so so these qubits, in order for them to sort of evolve together, they can't be, so I'll give you one example. Each qubit, you can think of having two states separated by, a double well, right? A double well potential. When you lower that barrier, they tunnel, for instance. You want them all to be tunneling the same. So let's say their barriers were different heights. Some of them might go into a localized regime, and there are a couple of other ones, and they drag it into a classical-like state. So they all have to evolve together. So it's critically important that within some percentage that we know that they're all uniform in their characteristics, right? And otherwise it's a complete mess. And so we have a very we had to develop this in situ tuning capability. We measure everything, and then there's a complex calibration routine that puts flux biases in all those loops because they're superconducting. Once you flux bias it, it's there forever. You don't have to redo it. Yeah.
Yeah, thank you, Eric, so much for this very informative talk, and thanks to all of you for coming. And yeah, stay tuned. There will be a series of interesting talks to come in this Quantum AI speaker series.